in some remaining time, I would like to make a foray into another little topic of interest, okay, which is the following. We described the full spectral phase function phi of omega. We described linear, quadratic, then third, fourth order chirp, right. And I brought up the point that these higher orders of chirp could be looked upon as some distortion or something that is gained on due to propagation. One can even say, okay, I take an unchirped pulse and in the process of processing this pulse through a medium, if you can, if I may use such a term, the process of propagating this pulse through a medium. Pulses cannot be frozen in time. Only in a lecture class, on a chalkboard or on a PowerPoint slide you can freeze them, otherwise they must travel at the speed of light. So, they are all the while propagating. So, they can suffer these distortions and changes whatsoever it may be, right. So, now we must therefore have some model for the propagation of pulses, otherwise we are lost, right. No matter we have this nice formulation, does not matter, but we are totally lost if we can't handle propagation, right. Or now that we are evolving a framework for understanding the way in which to treat pulses rigorously mathematically, we need next a way to mathematically treat, model and even deploy pulses into real media. How do we get there? That is the next step. That next step concerns treating and developing a treatment for the propagation of these pulses. We were in the frequency domain in the description of pulses. We quickly made a switch from time to frequency because I said, oh, we can do measurements in the frequency domain. So, therefore, let us switch to that, right. So, likewise we could stick to the frequency domain for modeling propagation as well. We can say linear propagation, that is the medium itself is linear and does not, and the conditions in which the pulse is propagating does not call for the use of nonlinear effects from the medium to the pulse. In reality, this is an approximation, either owing to relatively high local intensities in the pulse. What is the height of this peak? On what scale? These are all questions to ask. We have not defined the vertical scale at all in all our discussion. So, we have made a very simplifying assumption that it should not matter to us significantly in our descriptions, okay, which is true only for low intensities. How low is low? One has to answer that question in a rigorous way, which I will not do right away, but let us just say sufficiently low intensities or weak electric fields, we can afford to do this. Okay, you can already think of how low is low or how high is high by comparing the electric fields in this pulse to native electric fields inside of material media. For example, I need a scale that can come from the electric field that binds the active electron, the electron that responds to these fields in this condensed or atomic or molecular system, and then deduce therefore a measure for relative strengths. Okay. So, let us treat that as an aside, but if we have if we only need to be concerned about linear response of a medium, or if you are an engineer, you know you always you always first consider linear response or impulse response for that matter for the system, which then defines other characteristics, but first deal with linear response and then view everything else as corrections or higher order perturbations to this basic feature of a medium, right. So, if we know the electric field in the frequency domain, then what do I need to know about the medium, which is the blue box here, through which the pulse propagates? What do I need to know about this medium? I need to know two things. One is the refractive index as a function of frequency for this medium, and I need to know the absorption coefficient for this medium. Alpha is the absorption coefficient. So, where do these quantities come from? So, the absorption coefficient for a medium comes from the fact that a pulse does get absorbed inside a medium, right, as it propagates. So, we have essentially the electric field to be an amplitude E naught. E naught is all, amplitude is a function of omega, and we had exponent of I k z minus omega t. So, t is the time it's arises out of propagation and so on and so forth, right. So, so let me take the spatial part of this propagation, okay. For the moment, let me consider the spatial part. What is k? Is 2 pi divided by lambda times z, and if I may use this sort of a term, I say lambda, okay, is lambda naught the wavelength in vacuum divided by the refractive index, okay, times z, okay. If I take this up to be this quantity, then essentially the propagating pulse is described by this equation, okay, where refractive index, okay, let us write it like this, for a given wavelength, refractive index plays a role, omega, the corresponding omega plays a role, but then there is a, if I subscribe to this view and describe my entire pulse based on these, on all of this, lambda naught is fixed, there can be many lambda naughts constituting a pulse, omega depends on that, okay, because c is nu lambda. In this case, v, the velocity, the phase velocity of a particular frequency is nu lambda naught divided by n, where nu is the frequency, right. So, the point being that no matter what happened, this entire thing is cosine of something plus sine of some, I sine of something, and only the real part of that matters, right. So, in this entire formulation, what I am missing is what if this medium absorbed a part of the pulse energy from somewhere, for whatever reason it absorbed. Even transparent glass absorbs tiny fraction of light. That is why when there is enough sun, even glass gets hotter, right, and it stores that heat energy in some internal storages or degrees of freedom, right. So, by just introducing the refractive index alone in this form, I would not be able to capture absorptive phenomena. So, what do I do? Should I have another formalism for taking care of absorption and whatever or whatever not? What should we do? We are kind of stuck because we are now running out of parameters and I am running out of space on the screen. Alright, there is an elegant way out. Okay. Recall what we learnt about the basics of absorption if we did or whenever we did. If you did not, do not worry too much. This is all you need to know in a nutshell. If we had a medium of length L, okay, then the so called Beer-Lambert law, for what it is worth, it is called a law, but it is a nice elegant expression, tells us that if an intensity I0 is incident on this medium and it comes out as I after propagating a length through the length L of this medium, what is lost in the process can be explained away using this nice expression where you have an exponential dependence on the length of the medium, okay, and a quantity alpha. Now, this is going to create a little bit of trouble for us here, but I will call this alpha I of omega. So, every frequency omega, okay, will get absorbed. What is the so called absorbance of this medium? IL by I naught, this is exponent of minus alpha I of omega times L, right. Or in other words, this is essentially alpha I of omega is per length of the quantity log of I naught by I L. This is the absorbance, like the reflectance and transmittance, the intensity absorbance if you wish, or irradiance. This is a measure of intensity or irradiance absorbed per unit length of traversal through the sample. This is the other thing that we know about absorption of pulses. So, what does this tell me? But I also know the following fact: intensity is proportional to absolute value square of E, right. Therefore, here is a solution to my problem, that E, okay, E scales as square root of I. We have been liberally using that. Therefore, the Beer's law, in Beer's law there is no refractive index, or Beer-Lambert law there is no refractive index. If I take the square root of stuff here, IL is I naught whatever, I take the square root of the entire expression, then the electric field after the traversal by a length L is going to be proportional to the initial or incident electric field times exponent of minus a different alpha times L, this would have been equal to exponent minus the square root would simply have given a factor of half over here, right, times L, right. So, now we have two nice expressions. So, let me separate them out with a line. I have one this expression here and we have this nice expression here. You can pick out any of these guys, does not matter, or pick out this expression. Okay. Maybe I should use the highlighter, something like that. We can put these two together and say that look, the phase propagating through this medium, the phase part of the wave, okay, for a given frequency omega, for every frequency omega, the phase is modified by what is nk times L? It is just phase delay. For every omega, it is the phase delay. N times k, k is 2 pi by lambda, lambda measured in terms of the wavelength in vacuum, times L is the phase delay that the pulse has incurred. At the beginning, before entering the medium, L is 0. So, that is where the phase clock starts to tick. Whereas, this entire thing amplitude is now diminished by a factor exponent of alpha. Okay, so this I made a little error in calling this a different alpha. This is the same alpha, that is why the factor of 2 is there. I did not note that. So, let me keep everything consistent, sorry. Okay, I should have dealt with that better. It is the same, okay, it is alpha by, okay, let us use only one alpha everywhere. Let us call it in this entire session, let us call this alpha L. So, 1 half alpha I L, there is no need for this expression at all. So, we have for the amplitude part, the amplitude comes down by a factor of minus alpha by 2, where alpha comes from Beer's law, times L, the propagation length. So, now we have everything taken care of. We could have written this entire thing also in terms of an elegant, another elegant expression, where we could have said this is E in tilde denoting the spectral Fourier domain and Fourier domain, that this is the exponent of I times, here multiplying L, here multiplying let us say K L, here N plus n I times, let me keep track of the omegas too, n of omega plus n I times alpha of omega by twice k. Something like this, right. But let me make a quick definition then, as I will now introduce a new refractive index, sometimes unfortunately given the sign n tilde, owing to denote the fact that this is complex, where this is n, okay, n tilde of omega, which is equal to n the refractive index plus I times a kappa of omega, where kappa is derived from what we have here, that is kappa is alpha of omega divided by twice k. So, this gives us the notion of a complex refractive index, okay, right. because now I can capture the entire thing as E out of omega is E in omega exponent. Okay, I had a, if everything has a minus sign, then things change a bit. Then I should have had here, yeah, I should have had here also a minus sign, right? It's consistent, right? Then this would give me the whole thing to be n I minus I times L tilde times K of L. So, a complex refractive index. Allowing refractive index to have the freedom of becoming complex captures not only refractive, but also absorptive phenomena into the one number. So, typically actually in terms of materials physics or engineering, for every material at a given wavelength, we typically have n kappa values tabulated, but it is typically spelled out as n k values. Kappa becomes k. There is a slight misnomer, but when conjoined with the n, k of course means the imaginary part of the refractive index. Okay, so the nk values at for any material at every wavelength is a material property. Just measure, tabulate this once and for all and use it for every wavelength. Right. So, then okay, the whole point being, if we know this and propagation is linear, what do we care? All we care about is how the amplitude is distorted by the medium or changed by the medium for every frequency, and how the phase factor changes. If we have a full knowledge of these two, what can we do? We can take the pulse in the spectral domain, propagate it. In this case, multiply out alpha and n in the appropriate places and bring this out. If you have a medium, of course, this presumes that over this length L the medium is homogeneous. There are no variations of whatever kind. If there are, then one needs to know how alpha and n vary inside the medium, have a knowledge of that, and then do an integral or write a differential equation that can help sort this out, right. So, that is what we would want to do. In other words, we can also look at this as, now we have this entire thing, n is a complex number, we should know this complex number at every point, and then we can evolve a way to solve the problem of propagation. Well, pulse propagation is a very interesting and I would say important aspect of things. Okay. There are more sophisticated ways of dealing with it. We can do away with the approximation of linearity in the medium also fairly well, and we can deal with non-linearities as well, in which case the corresponding material coefficients should also be known. If I were to consider this a problem of modeling the propagation of pulse through a medium which is not necessarily linear, but whatever that is, we can capture all this into a nice elegant formalism. Okay, this is the basis for pulse propagation. This is not everything of pulse propagation. We just discussed yesterday how nonlinearities can make life very interesting for in the case of propagation of pulses. In this case, the medium is passive. Linear propagation of pulse is passive propagation of pulse through medium. The medium barely does anything to it except maybe absorb a fraction of it, okay, or and add some boring phase to it, let it accumulate and so on. But this boring phase is also what keeps all optical fibers going, where loss is kept very low by deliberate choice of wavelength, and you have the phase due to the refractive index and so on, and the contrast in refractive index between the so called cladding and the core leads to almost infinite propagation from end to end of huge long fibers with other say entities in the process like repeaters and dispersion compensation elements and so on. But the point remains that while linear propagation is great in communication, we need all that. We of course need even in communication, or otherwise in these scenarios for very short pulses on the femtosecond time scale, owing to the fact that energy is concentrated, pulse energy is concentrated on very short time scales, the intensities that are involved necessarily will push us to consider models beyond linear propagation. But for now we will stick to linear propagation, and this will be the basis for the linear propagation of pulses in a medium. With that we will stop for today and